So, I'm Ryan. I'm going to talk about what convnets look at when they look at nudity. So a disclaimer, this presentation may contain content which some viewers might find offensive. For example, the photo of Lena, which many people have only seen the top half of. Before I get into the actual talk, I want to kind of describe what Clarify does. So just to get a demo really quickly to see where I'm coming from and what we're building. So we're a neural networks corporation. We provide image recognition as a service. So for example, you take a picture of a boat. Our API will tell you things like sunset, water, dawn, dusk, boat, reflection. It will also tell you things like what colors are in the image. It will tell you if the image is safe for work or not safe for work, as well as things like faces. You can give it a different image, let's say, of some people. It'll give you some concepts: togetherness, love, outdoors. Safe for work, it'll find two faces. It'll give you some information about the colors in the image. You can also give us videos. So processing a video through a GPU can be done faster than if you were to watch it. And then you can see here's the parts of the video that have the concept, say, outdoors. Might be somewhere along here. And then maybe later on you see the word daylight appear, and less so over here. We have plenty of models. We have a model gallery. You can see things like celebrity recognition, color, focus, face detection. We provide embedding models for people who are more data science knowledgeable. And we also do things like travel, logo detection, wedding-specific models. And we also give you the opportunity to create custom models with our API. So here we took a bunch of photos from Instagram that correspond to photos taken from the window seat of a plane. And with a few clicks, so I take something like this, I can say click on it and label it as a wing, and then I can train the model. Training happens fairly quickly, and then I've updated my model to distinguish between wings, engines, and windows. And then I can search as well for a wing. I can search for photos of a window. And the check marks are labeled data. The things that are not checked are unlabeled data that were found using the model that we had just trained. And this has other applications. I have a baby cam. So Raspberry Pi is always videotaping my crib. If I want to know if the baby is missing, I can use my classifier to say the baby has not gone to bed yet. If I want to know if the baby sat up, I can use the classifier. Like every half second, it tells me that he sat up. When he goes to sleep, it will tell me that he went to sleep. And if he stands up, it will tell me that the baby is standing in the crib. And I can use this to get an alert. I don't need to because he will do that for me. But there's a bunch of classifiers you can make, and you can make them very easily. And this is what our company does. This is our product. But what I want to talk about today is more specifically one of the models that I've put a lot of work into is this safe for work or not safe for work model. And we do the whole thing with a neural net, but we don't really have to. Since this is not a new problem, people have been trying to moderate content for about 20 years. You can think about maybe 1996, the internet was just getting popular. Immediately, there was a ton of porn being uploaded onto everybody's sites. And then papers started coming out where they wanted to discuss how are we going to remove these nude photos from our websites that people are uploading. And the approach that they would do in 1996 actually makes a lot of sense. You look at color and texture properties to get a mask for skin regions. The skin mask is good for like all different types of ethnicities. And then you kind of look into a grouper that tells you that there's a bunch of skin. It's in the shape of a human. We know what a human shape looks like. And because we know what a human shape looks like, we can make a decision as to whether or not this is a photo of a human that's entirely skin. So here's like their features that they engineered by hand. You have like some skin that's like a segment. Maybe there's like a limb. Maybe there's two limbs. You find the face. There's like this guy's doing this. And then you can figure if that entire thing is skin, then that's probably a nude photo, and you should moderate that photo. Here's some examples of the activations that they took on some real-world data. So you can see like in some of these pictures, it's finding like correctly, this looks like a lot of skin. It's kind of a stick figure. We should remove that photo. And then sometimes it doesn't work. So here's like some bread on a table. It thinks that this is a leg, and this is a leg, and this is a segment. And it's not quite doing what it's supposed to do. So you have some false positives with this type of method. Every method will have false positives. But what I really like about what they did here is that they built this algorithm, they ran it on some images, and then they went back and visualized the features that the algorithm used to make a decision as to whether or not this image should be moderated. So in addition to building that algorithm, they built a visualization technique to understand and debug the algorithm better. And this has gone on for many years. There's no standard data sets in the field, but people hand engineer features to accomplish computer vision tasks for quite some time. So somebody had modified the sift features into something called hue sift, which is more specific to skin tones, and then they used that to solve the same problem. Here's somebody who did a lot of segmentation. Maybe they did Chan-Vese, maybe they did something else. Very complicated image segmentation on top of skin detection in order to remove pornographic web pages. And this gets really complicated. So here's something, I think this is 2008 this paper came out, and the features that they engineered was more complicated than what they did in 1996. What they say here is that for each blob in the image, they compute the area, centroid, the length of the major axis of an ellipse with the same second-order moments as the blob, the minor axis length, eccentricity and orientation of the same ellipse, the area of a convex hull fitted to the blob, the diameter of a circle with the same area of the blob, the solidity, the extent, the number of colors in the image, and the area of a face in the image. And then based on all of these features that they think make a lot of sense, you can get an ROC curve that looks pretty good on the test set that you designed to filter out the nude images that you might have on your site. And that's not unique to this problem. Image recognition has always used hand-engineered features. 1978, this is how you would identify, say, a human. You have a shape that looks like a human. You would look for patterns like this to find humans in hands. Things like that is how people would always do it. And if you keep pushing along this direction, eventually someone's going to get really good at feature engineering, and then you're going to solve the problem. And then you'll be done. It'll have the best thing that works. And this guy actually, I don't think that was what he was working on, but this was, so little Jonah Hill went to do something else. And yeah, that's not actually what happened. There's another way to get the same problem solved, which is a convolutional neural net. So a few years ago, it was discovered that these work very well. And a convolutional neural net has two operations that really matter for this talk. There's convolution, and there's pooling. So briefly, what a convnet does is you take an image, let's say here we have a boat, and you slide a little window with a particular filter along the image. Let's say you're looking for a vertical line. You find all the vertical lines with the vertical line filter. And maybe you have 30 filters. You have something for diagonal lines. You have something for horizontal lines. You have lots and lots of filters that are very, very low level, very simple things at the start of the net for the first convolution. Then, because you want to make things a little bit cleaner, you want to only deal with a little bit of invariance with respect to space, you have a thing called pooling. It takes your large stacktivation in a 4x4 grid and just throws away the other ones. And then you repeat that process a few times. That's why the network is deep. And you take the edges, you kind of run more convolutions, and you assemble them into things like corners. And then you assemble those corners into things like squares, circles, spirals, eventually wheels, faces, all kinds of stuff that's more and more and more semantically interesting and higher level, but with lower dimensional representations of your image towards the end. So if this is, say, 256 by 256, you have a very high number of dimensions in this image, but at the end you might have a 1,000-dimensional vector. And then on that 1,000-dimensional vector, any standard classifier will tell you if it's a boat, a cat, a bird, or a dog. So I built a network to do this, and one of my categories was not safe for work. One of my categories is safe for work. And I get an ROC curve that's really good. It's just perfect what you want it to look like. And that's great. So it sounds like I'm done, and we can ship this to production, and everything is fantastic. How did I do it? I took a lot of safe for work training data. I took a lot of not safe for work training data. And I ran it through a convnet. The demo network in this talk is going to be a pretty standard convolutional network. It's one layer different from AlexNet, 5 convolutional layers, 3 fully connected layers, 2 softmax outputs for safe for work and not safe for work, altogether a little bit under 70 million parameters. Nothing crazy. And something neat about those pictures and the semantic representations you get, if you look at this picture kind of closely, you'll see that the fireworks are close to the fireworks. The skies are close to the skies. The flowers are close to the flowers. And the way that we organized this photograph, this is a bit of an aside, was we looked at the convnet, we looked at the last layer. The stuff that was similar in the last layer gets put close to each other in that picture. So there's a lot of semantic information that's towards the end of the net before you make the prediction. Okay, so I have this data set, which I constructed based on what I think not safe for work means. And then I have a bunch of stuff that's safe for work. I have my network architecture. I have a test set. I train it with backpropagation. And if I was in academia, I would do this. I would get that fantastic ROC curve, and then I would publish the result. And everything would be great. I'd be done. But there's a bit of a problem here because as a data scientist at an artificial intelligence company, I'm responsible for actually making this data set. This network architecture, our CEO can invent those really well. But the actual data set depends on what I think NSFW means. So I do this, I use a neural net, I get a very good model that works extremely well on my test set, and then if I deploy it into production, I get a lot of emails back. So there's customers that are saying, I ran your model on these pictures, it didn't work, I'm getting tons of false positives, there's these other things that you never thought about that were never in your training set. And it's entirely out of sample stuff, but it still counts because in order to be a company that provides this as a service, we still have to understand images, which we weren't thinking about in the first place when I built the data set. So what I would like to do now is I'd like to go to my neural net. I'd like to say, okay, here's a picture. Why did you make the decision that you made about the picture that I gave you? And with those papers from 1996, they had a method to do that. But with neural nets, they're kind of a black box. You can't really understand what's happening once you've trained the neural net. So let's think of some experiments we could do. I want to answer the guy's email. I want to say, why did my network make that decision on that image? So one thing that you can do with any computer vision classifier is you take your image, and then you sort of look at the image through a peephole. So here's this photo of Lena, and if you could block out everything and just kind of slide around looking through the image, and every time you see something that's not safe for work, you score it a bit higher, you give it some red. Every time you see something that's safe for work, you leave it blue. And as you slide this around, the parts that are not safe, when you only see that part, is going to turn out red. So it sees this whole zone is the not safe zone. This is not. And you get these blobs of regions that look like you might want to pixelate those if you were trying to filter them from your website. Or you could try the opposite approach, which is you just kind of try to pixelate different parts of the region. If you pixelate the right thing, you score some points, and it shows you the blob of stuff that it was right to pixelate. So occlusion experiments are one standard way to understand what your classifier was activating on. And you can do that with a total black box, classifier. So I did this with our API, and we don't give away the neural net architecture in the API. It's just, here's an image, here's the tags, here's some code that makes those photographs. So with a total black box, not even knowing it's a neural net, you can do that experiment. But they're kind of blurry, and they don't really give me a ton of insight into what was happening. So there's another approach to understand what a convolutional network is doing, which is to go backwards and use something called a deconvolutional network. A deconvolutional network is a way to map the activations at high layers back down to the input. It's the same as using a convnet, but in reverse. So when you have a max pooling operation in your convnet, you have to undo that. So you have an unpooling operation. If you have a convolution in one way, you have a deconvolution in the other way.
Could you please speak a bit louder?
So a deconvolutional network works the same way a convolutional network does, but in reverse. So what you end up doing when you have a convolution on one layer and you're moving the activations backwards down to the image domain, you're going to deconvolve those layers. You're going to unpool your pooling layers. And what you can do when you have a deconvolutional network is you can take an image and you can take a prediction And then you can go backwards from those activations down to the image space, and you can ask it what features in this image were most important for the prediction that you made. In this talk, I'm going to use this as a probe to look at a trained neural net and understand why it made a prediction. This is a bit of an abuse of the word deconvolution. You can find some GitHub debates about it. Deconvolution has a technical meaning, which often shows up in image processing used for deblurring. And originally, a deconvolutional network was an unsupervised method that was used to make a competitor to, say, sparse coding to represent an image through like a stack of learned filters. So well, I'll just get past that. But the filters that people often design for convolution and deconvolution, people do things by hand. They do wavelets, curvelets, framelets, shapelets, shearlets. People have designed a lot of low-level image filters over time, and a deconv net originally was just to learn these filters automatically. But so let's go back to the deconv net. The way that you actually solve the deconv problem is as you move from, let's say, the layer below the pooled maps, you do a forward pass of your image all the way until you get your predictions. As you move your image through your convolutional network, what you do is you take all of those max pooling layers and you save which element in the 4x4 grid was the one that was the max. You save the location. So if you had something like, the second of the 4 was the maximum, you just save the number 2. And you save all these switches because when you have to unpool, the operation of taking the max is not invertible. So you have to save that during the forward pass. And then the backward pass, you fill in the remaining things with 0, and you go back to the thing that was saved. So animation of what that means. If you start with your feature map, maybe this is the highest activation after a convolution, this one or this one. Then you do a max pooling operation. It takes this 4x4 grid down into a 2x2 grid. And then it takes the highest activation, and then this would go into the next layer of the convnet in the forward pass. When you save those switches I was talking about, you would just save, this was the highest, here's the location I saved. This was the highest, that's the location I saved. So when you have to solve the unpooling operation, you just say, okay, whatever value was here goes back into the unpooling. These I threw away, but those are 0. And surprisingly, that's like enough to get detailed feature maps. So when you do a deconvolutional network and you move the activations down to the base of the net, you're able to visualize and understand your convolutional network and what makes it activate. So let's take a look at a standard network not specific to NSFW, which is going to have a deconv net used to visualize the features that it thinks about. So this one is just for a regular ImageNet network. The first layer of the network is learning edges. These look like your standard edge detectors that people invented by hand. The second layer of this network, using this deconvolutional process, we have identified things like circles, things like sequences of lines all together, maybe like parts of wheels. And by the third layer, we start to see things like faces, or almost faces. We start to see like a dog face up here. We'll see a child's face down here. We can see things like a wheel. And we can see a few other interesting things in this chart. I think there's this looks like part of a monkey. And that's only the third layer. We have 2 more to go. The fourth layer has even more semantically detailed features that are being learned automatically by the network. So here you have a larger field of view because you're at the top of the network, and you can learn, a much more detailed dog's face by assembling those previous ones. I guess there was potentially flags or some other type of wheel in here. Lots of dogs. ImageNet has dogs. And then by the end of the network, this is the kind of information that goes into that last classifier. That could be any kind of thing. It's always going to be like a logistic regression, but it could be anything like a random forest, whatever you want to do with the embeddings. And these features that you've learned are very, very detailed and learned automatically. And you can see like, versus a regular face detection, look at what we're able to learn with the neural net. So that's a general neural net. This paper that has these pictures in it is reasonably like old, 2 or 3 years, and this is a standard data set with a standard neural net. Let's look at the one I was talking about earlier. So here we have the same architecture that I just did, but all I did was change the data set to be safe for work or not safe for work. And instead of spending 20 years of computer vision research trying to engineer features by hand that would tell me what kind of images are going to be moderated, what kinds are not, I'm just going to give different data to the neural net. And at first, it starts to learn edges. And then it starts to learn these like stripes, multiple edges in a row. It starts to learn these kind of like pink circles and some green circles. They're important. And then by the time you get to the third layer of the net, you start to see things that are actually different than what the other net learned. So over here, you start to see something looks like maybe a fold in an arm. You see somebody's chest. You can see faces, you can see people's behinds. And I never had to tell the network to do this, I just showed it images. The fourth layer of the net is more detailed and higher resolution. So something over here, it's like, again, somebody's behind, you have somebody's face. And then by the fifth layer, it starts to get more difficult to zoom, and you start to see like entire regions which the network is understanding as important to filter. So maybe this one is something that it's definitely going to want to remove. And then by the time you get to the end of the network, you've seen very, very detailed, very high resolution features, which are much, much more sophisticated than the things that people were developing by hand 20 years ago. Because those stick figures that you would see in the paper from 1996, unless you were very, very creative and very artistic, you would never have actually put something together that's a filter map as, as detailed as something like this up in the top. It would take much more time to engineer just one classifier to solve just that one problem. And you can also ask the classifier other things. You can give it images that are safe, and you can ask it, what about this image would make it not safe for work? So I give it this picture of Barbara. Barbara's like another version of Lena, which doesn't have any controversy. And you can take the photo, you can run it through the neural net, you can set all the activations to 0 except for the one that says safe for work instead of not safe for work. Then you deconvolve those back down to the image domain, and you can say, how would this image have to change to make this image look not safe for work? And the network learned that this image would be less safe for work if it had red lips, or if you added more red to the lips. This image would be not safe for work if you made the top of the cake look more like that. Here's from James Bond. This image would be not safe for work if you had red lips. There's a little bit of activation here in the middle by the bikini, and then the navel was really important. So that's something that's really interesting that you can learn about from the net, is that when I gave it these images to train the model, probably every time I gave it an image that was not safe for work, somebody's navel was exposed. So then it learns to like trigger on that in addition to triggering on things like red lips, which might mean I'm overfitting, or maybe that's right. But if it's not the kind of thing I was going for. It's just something that the network learned accidentally. This photo was a little blurry, but it did zoom in on here and here. And as you train the network, you see that initially the features that are learned are kind of noisy. They get better through different epochs. And then by the time you get to the end, again, it zooms in on here and also on the navel. So to recap, in 1996, this is what we could do for like mapping out these kind of photos. You would design something by hand, it would look that well. In 2016, we're able to automatically learn classifiers with that much information in them. Okay, so that works really well, and I don't think we're going to get better like feature maps by hand or with better neural nets. I think for this, we're pretty good. But there's a lot of other stuff that goes into content moderation that is beyond just the pixels. So here's a photo of George Bush. There's a lot of context in this photo that makes this photo really interesting to any human who's looking at it. So it's people, adult, man, facial expression, to portrait, elderly, happiness. It's a bunch of stuff to the computer, and it's not interesting to the computer. It's just like stuff. But to anybody who's like, knows who George Bush is, knows that a politician is supposed to be kissing a baby, knows that he's not doing it successfully, his facial expression is like gross, like the kid is crying. It's like a very funny and interesting photo, and like the computer has no idea why this photo is significant. And you have something here, there's like, it's pinching the airplane, and that's really neat, and the computer has no idea, even if it has very detailed like features that it's using to understand. Here's the interspecies high five. Again, this is really cool, but the computer has no idea. And if you're doing content moderation, you can take a photo like this. So a lot of people want to remove things that are sort of upsetting to look at, sort of the not safe for life versus not safe for work. And something like this, you often don't want that to appear on the homepage of your site. I mean, The Guardian did, but because of all the context, this is a very upsetting photo for a lot of people to see. Everybody has seen this one? Okay, so I'm not going to show the whole thing, but the computer doesn't understand anything beyond water, people, action, man. And the only way to actually get it to really know that this is something you should moderate is to use extra context, which is kind of beyond the scope of what we can do, even though the features that we learn are very good. Customization, I talked about a bit. And I actually thought I took those out. Yeah, okay. So, time for questions. Oh, do I have to?
Unusual.
Hi. So the work of Ian Goodfellow, he does a lot of stuff with these adversarial training where you'll take the image, you'll find out what makes it classify wrong, and then add that information back to it. Have you tried doing a similar approach where you take a safe for work image, find out the content that makes it not safe for work, and then adding that to create an adversarial, like basically like a GAN type technique to improve the generalization of the network?
I have never tried to do this with GANs. I've definitely seen a few interesting things where people have done the same kind of stuff with GANs. I've only done this with a dconvnet, so.
Thanks.
I think I have some time, right?
Yeah, like 10 minutes.
Okay. Yeah. Oh.
I was just wondering, how large was the data set you were using to train this particular network?
I had about 5 million images. I had 5 million images altogether, so I held out 500,000 to make that ROC curve for the one that was in this talk. In general, we train on a lot more. But, for this net, I think that the way the parameters work, it's 224 by 224 is what goes into this particular net, but your architecture kind of tells you what those should be.
Sorry, so, oh, sorry, over here. So in some of those earlier papers, color and skin tone was really important in addition to shapes. How important was having color images to this? Have you tried doing the same experiment with black and white only images?
So it works okay in black and white, not intentionally because I threw a bunch of black and white in the training data. That being said, if you look at Robert Mapplethorpe photos, you can really get this wrong all the time. So artistic nudes, something about them, it just doesn't work as well. And the neural net, it's interesting, like color is kind of destroyed by like the first layer because you only have those 3 channels to start with, and then as soon as you move into the second or third layer, you have a whole bunch more channels than just RGB. So the notion of color disappears, and the only way to normalize for that is to augment your training data.
So it seems like we've kind of taken the emphasis off of feature engineering, but you can still find these kind of interesting chandelier-like examples in your out-of-sample, out-of-validation set. Does that mean that maybe an effective way to improve models is to continually use them in a sort of semi-automated way to find bad examples?
Yeah, that's actually something that we do and think about a lot. Active learning is great, and active learning is kind of really, really great for neural nets because Mechanical Turk can do your feature engineering for you. Like people just click on stuff, and then they're like inventing the features you need. So that's great.
What was the size of your neural network? In terms of the nodes, in terms of the layers, and so forth?
The one I did for this talk was 5 convolutional layers and 70 million parameters. Nothing crazy to make those pictures. I imagine if you did like Inception v4, you could also get those pictures.
Yeah, so your 1996 picture, not yours, but the one you showed, with the bread on the counter, that was not safe for work, right? Because of the mechanics of the analysis.
Right, that was a false positive that they report in their paper.
So is that well known in the diagnostic community as an example?
That bread picture,
Yeah, that specific one.
I
Is it something you came across, or is it like a standard, here's what didn't work?
the pictures I saw in the paper from 1996, I have not seen those in other papers. It's not like Lena or Barbara. Yeah.
I was just wondering if that was the first instance of food porn.
So you showed the safe word, like a binary classifier network, and then a labeling network, right? And it kind of seems like if I had both of those, and I had something that was not safe for work, but didn't have any people in it, then you kind of cross-train against between them, right? Would it be better to kind of keep those as 2 separate networks, or could you have a single network that did both the classification and the labeling and train it all together and get better results?
I don't totally know. You can combine a lot of categories into a single net. Like our general model has 11,000 categories that it predicts, that's a big vocabulary. But at some point there is like, you start to stress the capacity, and if you want to understand something like, let's say, make and model of car, or you want to get very, very detailed, like user-specific NSFW filtering, then you only have so many parameters, and if you start to cram a bunch of information about make and model of car into the same network that's also doing like photos of bikinis, you get to have some, like, I guess, underfitting problem. So the question has no clear answer, but intuitively I like to kind of keep them separate if I have enough data to make one. That way.
You could run through 2 of them and then take the outputs and plug that into a third network, no problem, right?
Right. Right. So So to your first question, if you do the occlusion experiments, you get kind of blurry information about where the network was activating. I would never have been able to see something like red lips or navels are important to the network if all I had was occlusion experiments. They don't give you the same resolution that you get from the deconvolutional network. To your second question, to improve this, I run the network, I get false positives. Hopefully I can use those to find stuff that's like that, send that off for labeling, run the thing again. Just always update this thing based on humans in the loop. It's kind of, this problem is a little bit difficult for humans in the loop because the people who are in the loop are looking at these kinds of photos all day and they don't like it. So, yeah.
So what kind of things are you working on to make these models understand context?
So right now, the big push from me is to make it do customization. Because we do run into lots of problems where somebody has all of the photos on like a dating website is people of a certain ethnicity, and we just have to be accurate for that website. That's going to be more customization than this extra context. In order to do that extra context, I really don't know. Like the Facebook murder that just happened and like nothing caught it, Facebook runs tons of neural nets every time you update a photo. But that was shown to hundreds of thousands of people before anybody noticed it. It's a much harder problem, and I think it's like you could do a PhD on it. Yeah. Right, that's the part of this that's hard. So what we're doing with that is I showed that demo where you can customize a model, and I had like a general model. I customized it to do airplane wings or baby is sitting, stuff like that. This model, you can almost, I mean, we have to do some back-end work. You can also customize this. So it still has all that understanding of human anatomy, but then to actually see, do I flag this as porn, sexy but not porn, safe, or something else? Like, that's going to be like on the user to just kind of give it a few examples of each category, and then the network will adjust itself to work in that particular context.
What about the accuracy you achieved in terms of the sensitivity or specificity?
Right, so the accuracy I got with that ROC curve, it was amazing. But the problem that I have as a data scientist is that the accuracy can be extremely good because the data set that I'm using to test is really easy. So then I have to keep going back in this loop of like re-engineering my test data set and my training data set until I have accuracy that looks bad. And then that has to be labeled by hand. So the ROC curve I showed, I don't know, it's like 200% accuracy. But it was not, Well, that's the issue, is that the data set that I test on, I can very easily hit like above 90% on all these things. But if if some of the test set is like all very obvious, like shiny porn, and the other stuff is just cute dogs, that doesn't really tell me a whole lot. When I put this on extremely like borderline images, like everything is PG-13 or like R, then I start to see lower levels of accuracy. But at the same time, when I look at the misclassifications, I personally am also not sure some of those things where they should be. So the problem that I really have isn't getting my standard evaluation metrics to look good. The problem I really have is making sure the data set that I use to train is representative of what our customers are going to care the most about.